Thank you very much for inviting me. This talk is my Caroline Herschel Prize talk. You can see a longer version of it online, recorded by Bath University in November. And I'll give this one a little bit fast so that we can have more time for interaction and we can free up the room within the hour. So, to do astronomy, you don't need fancy equipment. People sailed the Pacific using nothing but their eyes and their knowledge of the motion of the stars. Now, that being said, new technologies can herald new discoveries. For example, the moons of Jupiter were discovered by Galileo using, oh, will that work? Nope, that's not going to work. Yes, okay, I have to click, fantastic. The first telescopes allowed Galileo to find the moons of Jupiter. It was not possible before. And the invention of photography brought astronomy into the Industrial Revolution and allowed us to perform the first few large-scale sky surveys. In the second part of the 20th century, the invention of semiconductors allowed people to start controlling electricity on a really small scale, which turned computers from room-sized objects to things that fit on a desk or a lap. It also allowed people to make devices that turn photons into electrons. That's the digital camera. Those are the things that are now in telescopes. Now, the second part of the 20th century also brought about rocketry, which is very interesting if you want to make a telescope, because it means you can send your telescope out and away from the atmosphere. The atmosphere is a big, beautiful blanket that protects us from some of the harshest radiation in the cosmos, but it also gives us a blurry view of the universe, and it shields us from some of the very interesting wavelengths that stars and galaxies make. Now, some of the most famous telescope pictures that you've probably already seen are the deep fields. Here we've got a cropped version of the Hubble Ultra Deep Field. And in this cropped, zoomed in bit, you've got a few, maybe 150, 200 galaxies. And this is 100 times, this whole bit is 100 times smaller than the moon. Now, deep fields are very impressive. They were a gamble when Hubble started doing them, but now they are routine in astronomy. And obviously, when James Webb Telescope went up in December 2021, it started taking a deep field relatively quickly. And in 2022, we got beautiful pictures like these. Again, you can see loads and loads of galaxies and even a couple of stars in the foreground with the classic six-spoke diffraction spikes from JWST. Now, the reason for this introduction is not just so I have an excuse to show you some of the most exquisite images that we have in astronomy, but also to really impress upon you the fact that the history of discovery in astronomy is the history of a partnership between people and their machines, between people and new technologies. And that's the theme that I want to explore with you today. Right. Now, my job is very cool for many reasons, and one of those reasons is that I get to travel the world. And last June, I was in Chile to observe at La Silla with the New Technology Telescope, that tin can you see in the background. Now, the most observant in the room and on Zoom will notice there's a lot of clouds in that sky. Not ideal if you're trying to observe it, but fortunately, very quickly, those clouds were blown away by extremely strong winds that made it impossible for us to open the dome, lest we damage the telescope and the instruments within. So I was awake at night with plenty of time to twiddle my thumbs and play with my phone. And so I took pictures of the night sky with my smartphone, which is on that table right there. And this is a 5-minute exposure taken with this device. And what's really interesting to me is that you can see these beautiful clouds here, which are not clouds in the sky, but clouds in our galaxy, clouds of dust and cold gas that obscure our view. Now, here is a slightly nicer picture of the Milky Way taken with an actual camera, not just a phone camera, and here you can see colors. Now, those of you who have been to a dark sky reserve and looked up at the night sky with your own eyes will know that the sky does not look like this, not to our eyes. And that's because your eyes don't take 5-minute exposures, right? Your eyes can see a few thousand stars at best, at the best of times. A telescope like the one that our team uses, like Atlas, can see 1 billion sources. And of course, a camera like this can see somewhere in between, maybe a few 100,000. Now, a billion of anything is very difficult to picture, but I need you to understand the concept of these really big numbers and have an intuition for it. So I'm going to try and give you an intuition for this using time, because time is something that humans have a really good conscious intuition for. A few thousand seconds is the time that it will take for me to give you this talk. A few million seconds, or a million seconds, I should say, is over 11 days. A billion seconds is just under 32 years. So a billion is a massive number if you have to actually look at every single one of these sources. And because the sky is so big, it's a very interesting challenge for astronomers. Now, because it's so big, not only is it really big, but it's also ever changing. Betelgeuse is a beautiful example of that. You've got Betelgeuse there, the red shoulder of Orion, and its interesting light curve with the great dimming event of 2019. Now, variable stars are probably some of the easiest variable things to capture, but they're not the only things that make the sky interesting. We also have comets and asteroids, and we have some of my favorite explosive transients. Now, I'm not going to have time today to go over all of these different kinds of transients. The main point of this slide is to showcase the kind of timescales on which these explosions evolve on. The amount of time it takes for these light curves to change significantly, and therefore the amount of time the cadence on which you would want to observe them to be able to study them. Those are very short on the timescale of the universe, and even short on the timescale of a human lifetime. And this poses a problem for us because not only do we need to survey the sky across its vast expanse, we also need to survey it over and over and over again. We need to survey it across space and also across time. So that's why we build sky surveys like ATLAS, the Asteroid Terrestrial Impact Last Alert System. Now, ATLAS is funded by NASA mainly to find and track near-Earth asteroids, but it can find other things along the way. Now, to find these asteroids and other interesting shenanigans, it has 4 units, 4 telescopes scattered across the world, 2 in Hawaii, 1 in Chile, 1 in South Africa. And this gives it a sort of 360 view of the sky. But again, having a 360 view of the sky is not enough. You need to be able to do the observations over and over and over again. And so ATLAS has a very large field of view. Now, in this slightly overwhelming dashboard of one of our ATLAS units, you can see here some of the last exposures that it took, some of the last images that it took. And here you can see its footprint across the sky. Now, remember, cast your mind back to the Hubble Deep Field. The images that I showed with all those galaxies were about 100 times smaller than the moon. On these exposures, the moon would be something like this. So really, really, really small compared to our field of view. So this allows us to find not just the cool near-Earth asteroids, but also things that go bang in the night sky, the kind of stuff that I study. Now, I could talk about these for over an hour, but this talk has many other topics to cover, so I'm going to focus on 3 kinds of explosions and why we want to study them. The first one is going to be one that you've probably heard of, supernovae. Now, supernovae, the word at the very least was coined in the early 1930s, and in the last 100 years, astronomers spent a lot of time creating subcategories of subcategories of subcategories of supernovae. But today, there's going to be only 2 kinds of supernovae: the low mass star supernovae and the high mass star supernovae. As you may know, stars are separated into low mass stars and massive stars based on their initial mass when they start burning hydrogen. If they're born with less than 8 times the mass of the sun, they're low mass stars, and they will die as white dwarfs. They will burn hydrogen and then helium, and then their core is going to be made of carbon and oxygen. They're going to shed their outer layers, and they're going to leave behind a white dwarf. Now, these white dwarfs have a very interesting characteristic. If they reach a mass of 1.4 times the mass of the sun, they explode, and they give one of these supernovae. Now, these low mass star supernovae are interesting for 2 reasons. First of all, they are the main source of iron in the cosmos, and iron is very important for you to be able to breathe. These supernovae are also very interesting because they allow us to track the expansion of the universe, which gave rise to a Nobel Prize in 2011, so very interesting for a lot of people. Now, the massive stars are my personal favorite, and they're a little bit different. They explode when they die. So massive stars, when their core is made of carbon, they're massive enough and hot enough to ignite the carbon. So they ignite the carbon and they make oxygen. And then they ignite the oxygen, and then they ignite the neon. And then their core is made of iron. And iron is the most stable element in the universe. You can't fuse it or fission it to create energy. So at that point, the star is essentially screwed, and it's going to collapse under its own weight. It's going to create a neutron star. In this case, you can see it right there in the middle. And sometimes a black hole, but most of the time, neutron star. And then the outer layers fall in towards the neutron star, bounce off, you get a shock wave, you get a big explosion, you make a bunch of oxygen, calcium, and other intermediate mass elements. Now, I'll point out that this picture is a real image. This is a stack of 5 different wavelengths taken with 5 different observatories. The blue thing there with the pinwheel nebula is Chandra X-rays, the same X-rays that allow you to see your bones. It's not CGI, it's not AI. It's a little bit touched up, but this picture cost billions of dollars/euros to make. So let's just appreciate it. Right, so supernovae, very cool, and plenty more to say, but not enough time for it. Now, kilonovae are like a second little bit of drama for the neutron stars. So the neutron stars created in supernovae can go on to do more interesting stuff if they have a friend along the way. If they get a little too close to that friend and they collide, then they create a kilonova explosion. Now, it's actually pretty common for massive stars to have a friend, or to have several even. So if you've got 2 massive stars next to each other and they both go through their supernova, you're quite likely to get a binary neutron star. Now, if the conditions are right, that binary neutron star can then collide. And the way that it collides is that the orbit decays because of the emission of gravitational wave. So I don't know what degrees you're all doing, so I'll just give a very quick analogy that's pretty commonly used for the fabric of space-time, where you imagine the fabric of space-time as a literal piece of fabric that you have tight and nice and taut, and if you put a ball bearing in that fabric, it creates a little well, a little divot. And so if you launch a coin near that well, it's going to spiral in. But if you've got 2 massive objects, dense objects next to each other in that fabric, well, the potential well is not going to be round, it's going to be peanut-shaped. And so as they spin around each other, and as that potential well spins around, it sends waves wobbling around the fabric of space-time. Now, better than my artist impressions, oh, Lord, be with me. Come on, Ed, you gotta do better, man. First of all, power. Excellent. Now, come on, try harder. I am connected to Ed. Try harder. Hell yeah. Let's go. Very nice. Here you can see gravitational waves because they are distorting the light in the background. You've got a black hole and a neutron star spinning around each other, and as they emit these gravitational waves, it takes energy away from the orbit, which brings them closer and closer and closer together until they merge. Now, this was an animation, and there's a beautiful ring down as well. Now, this was an animation for a neutron star black hole merger captured in 2019 by the Osgrave team in Australia. But another picture that's quite interesting to see of 2 neutron stars merging, this time without the gravitational wave, is to see how they get distorted as they get close to each other, because that distortion is what allows you to get a nice little bit of ejecta that makes them shine across distant galaxies. So you see as they get closer to each other, they get tear-shaped, some of the material merges and some of it gets launched out into space and forms an accretion disk around the hypermassive neutron star. Now, a jet also gets launched by that accretion disk, and that hypermassive neutron star eventually collapses down to a black hole. And this ejector is what we astronomers looking in the optical with our telescopes can actually observe, and that you can sort of see in this artist impression. And this ejector is also what creates very interesting elements like platinum, gold, silver, rare earth elements that you need to make technology. Now, the last cool event that I want to talk about is tidal disruption events. And that's where the hungry black hole of the title of this talk comes in. I'm going to grab my phone because I don't know what time it is and I really don't want to go over time. So these tidal disruption events are what happens when a black hole is minding its business and a star gets a little too close for comfort, especially for the comfort of the star itself. And we're going to use another beautiful video that I did not make to illustrate this. So we've got a black hole, interstellar-like. They don't all look like this, but it's nice to have a beautiful image. And we've got a star coming in hot. That star is normal. It's not a neutron star. It's just a star. But as it gets too close, it gets spaghettified by the gravitational well of the black hole. And as it gets very close, it gets fully disrupted. Now, I'm going to pause it here because you've noticed, oh, for God's sakes. Whoop, come on. There we go. And it gets bright as the material gets close to the black hole. That black hole getting bright is not the black hole getting bright. It's the material coming back onto the black hole that is basically a victim to a space traffic jam, if you will. Black holes are not magical hoovers. They can only accrete matter so fast. And so as the matter is falling down towards that potential well, but cannot accrete fast enough on the black hole, it settles onto an accretion disk and it gets really hot and therefore starts emitting very interesting lines that we can see from very large distances. Now, these tidal disruption events are interesting because they allow us to probe black hole physics, like the spin of black holes, the mass of black holes, in a way that wouldn't be possible otherwise. Black holes are really annoying and elusive like that. They're impossible to make in the lab, and they're very hard to see. So tidal disruption events is one of the ways that we can probe how they work. Now, the main point of discussing these three types of events is to make it clear to you that looking at these shiny explosions isn't just fun, it can tell us about different aspects of how the universe works, the origin of the chemical elements, the expansion of the universe, the physics of very compact objects like black holes and neutron stars. But if we want to understand these topics and study these transients, we first have to find them. So, little change of pace in the next 10 minutes. Before we get back on the train of transients, can you spot the difference between these two images? This is a little zoom in on one part of that image of the Milky Way that I showed you earlier, that I snapped with my phone when I was bored on the summit of the mountain. You may have noticed that this picture is blurrier than this one. You can actually see the pixels in this one, the squarey pixels. Now, I was very surprised to see that this picture is the raw image that my phone captured, and this one is the JPEG that it saved. And the reason I was surprised is because I expected the JPEG to be worse than the raw image. JPEG is a lossy type of compression, therefore the JPEG should be worse than the image that it JPEG'd. Clearly, it looks like there's more pixels in this one. So what happened? Well, it's because my phone is not, and my camera is not just a simple camera, it's a smart camera. There's software in it, software that uses magic maths to add more pixels. It's basically generative AI to make it look like I've got a nicer camera than I actually do. So, maybe, do we have time for audience participation? Go on, I'll give it 2 minutes. What is AI? Let's have some hands raise up. Otherwise, I'm going to pick volunteers. Go on. Cute, love it. Artificial intelligence, correct. Technically correct, the best kind of correct. What is artificial intelligence? There's no wrong answer.
Machine learning.
I love you. I love you. Yes, absolutely. The reason I love this answer is because I think it is the more right answer that we can give to that question. The word AI is everywhere these days, and the word AI means very little. It has a very long history that is entrenched in humans being humans rather than having a specific, pointing at a specific kind of technology. For the rest of this talk and the kind of science that I do, and really for every application that you see online, most of the time you can replace the word AI by machine learning. You can replace it even by statistics. Now, of course, statistics does not sound nearly as exciting as AI, but it is what we're doing here. What we're doing is we're trying to teach a machine to do something. We're trying to learn behavior. And the way that we do this is that our machine is going to learn a function. Now, there's not going to be any maths in this talk, not because I don't think you can handle it, but because this talk is meant to be given to very broad audiences. So we're going to go with analogies today. A function can be compared to a DJ deck. Now, I don't know how these work. I've never had one in my hands. But what I know is that you put music in, you turn the knobs and dials, and a different kind of sound comes out. It's a pretty good analogy for a function where you put numbers in, twist some parameters, and different numbers come out. Now, in machine learning, the problem is you've lost the manual. And you don't know what the knobs and dials are doing because everything's rubbed out. So you've got to learn how to use your function. You know the inputs that can go in, and you've got good examples of what the answers should look like. And with this, you can play with it and learn how to make it work. Now, you may be familiar with this comic, although that's nearly 10 years old, so maybe this is the first time you'll see it. This is from XKCD, where you've got a guy standing on a pile of maths and another person next to them saying, this is your machine learning system. Yep, you pull the data into this big pile of linear algebra, and then you collect the answers on the other side. What if the answers are wrong? Well, you just stir the pile until they start looking right. And frankly, 10 years on, it still feels very true. Now, the reason I think people like the word AI, or at least are willing to use it, is because when they see a computer or a machine performing an action they don't expect a computer should be able to make, or when it's performing in a way they don't expect a computer should, then they're happy to call it artificial intelligence. But the problem is our expectation of what machines can do really changes over time and with culture. An example of this, I think, is computer vision. Computer vision is a big part of machine learning, but it is also something that I think people wouldn't call AI these days, because you take it for granted that Facebook can recognize your nan in family pictures, or that a speed camera can flash your car, read your number plate, and send you a fine automatically. Now, computer vision for a long time was the stuff of science fiction. Something you'd only see in movies where there's a locked door and they would scan the eyes and the fingerprints to let you in. But it's been a long time since the 80s. And in the 1990s, convolutional neural networks were becoming really, really performant. In 1989, the first decent CNN able to read handwritten digits came out. And it was the first author was this guy, Yann LeCun. By the way, the reason this GIF looks like this is because it is, I believe, from the late 90s. I literally found it on that guy's website. So it's still, I think, a very good visualization of how CNNs work. By the way, if you don't know what these words mean, it's fine. You don't need to. Convolutional just means a fancy filter, neural network, just a kind of function, a bunch of knobs and dials that take input and give you an output. Now, in a CNN, the convolutions are filters that basically take your image and turn it into an abstraction that makes sense for the computer. You can see it here in the first layer. You can see the different filters being applied. Some that enhance the top edges, some that enhance the bottom edges, some that enhance the body of the digits. In the first layer, it still makes sense. In the second layer, the digits are a bit hard to see. And in the third layer, you really can't make them out, not as a human. But that's the abstraction that's needed for the computer to make sense of it. Now, computer vision had a bit of a lull for 10, 15 years, and then things got really good really fast in the 2010s. And that's because ImageNet, a data set, came out of 1.2 million images, labeled images. And what these people did is that they put that on the internet and they said, go, make your algorithms and try to beat humans at image recognition challenges that we'll set every year. In 2011, sorry, we already had the first computer beating a human. And in 2012, we had AlexNet, very famous deep learning network that won the competition by such a large margin that it was a big factor in the deep learning revolution of the mid-2010s. Now, the reason I'm pointing out Facebook AI Lab here is because it's one of the tech giants that kind of hopped on that deep learning trend in the mid-2010s, but also it's not necessarily the best one or the first one. The reason I'm pointing them out is because they chose the word AI Lab for their team. At the time, AI was not a particularly in vogue word to use. It still had it still stunk a little bit from the late 20th century where it was overused and it didn't deliver on its promises. So basically they reclaimed the word AI, and here we are 10 years later using it everywhere. Now, the point of this interlude is to make the point that machine learning breakthroughs, at least in recent history, have come from two things: access to data and access to compute. For computer vision, it was a perfect storm. By the early 2010s, we all had social media accounts and we all had cameras in our pockets taking pictures of our faces and posting it on the internet. And compute was getting really good and really cheap because of the video game industry and the CGR industry, and GPUs that are great at linear algebra were becoming more available and cheaper. But going back to the astronomy, what that means is that we could teach computers to look at images and do our job, or at least some of our job, which is really nifty. If you can take your pictures and you can use maths to train your machines, then it can free up some time for you. Can you spot the difference between these two pictures? Let's focus in the middle. You can see there's a little fuzzy thing there, there's a little fuzzy thing there. That's the before picture, that's the after picture. Now, it's a little easier to see if I subtract the before from the after. And there you can see there's a supernova shining in there. Now you can see it just about in this area of the plot, if you know where to look. Now, this exercise is called difference imaging. It's what we do with our sky surveys. We've got 1 billion sources. We take the difference with a reference image and we see if something has changed. That's how we spot the new transients. The problem is difference imaging can go wrong, and it does so quite regularly, a little too regularly, if I'm honest. If it's not as easy as taking a difference, the astrometry is difficult, and if you have a crowded field, then you can find yourself with a lot of non-existent sources shining in your difference image. So you need to be able to handle this problem, which is really a needle in the haystack problem. With Atlas, we get tens of millions of these differences flagged a night, but only a handful of them are real, genuine transients that we care about. And it's absolutely impossible to give this amount of work to people. That means that we have to automate this work. Now, automating this work doesn't start with machine learning. Machine learning shouldn't be the first thing that you do. It should always be the last thing that you do when everything else has failed. The first thing that you do is basic cuts. The details of them I'm not going to go into, but it's as basic as saying, do we have several images at one spot that show a bright difference? If yes, then it's less likely to be garbage. The next thing that you do is you cross-match to your existing astrophysical catalogs. For example, I know that Betelgeuse varies. I'm not going to flag that one every night if I'm looking for supernovae. You know, it would be a shame to rediscover Betelgeuse every day. So you can take those out of the stream using catalogs that you know. And once you're done with this, you've got a few thousand objects left. And you can pass them through a CNN that does a very nice job of removing the bulk of the garbage. So that CNN was written by a PhD student in Queen's University Belfast, and it's been removing about 98.5% of the garbage we've got left over after the cross-matching, which is nice, but it's not quite enough. When you're done with this, you still have a few hundred things to eyeball, and eyeballing here is a technical term. And the eyeballers have a very tedious job because what's left is still over 85%, nearly 90% garbage. And before I joined the team, they were eyeballing between 150 and 400 objects a day. And the reason things were not automated further at the time is because automating this task is difficult. Eyeballers have a complex task ahead. They look at light curves, which frankly often look like just one data point and a bunch of non-detection. This is time and this is flux. You can't read the axes, but you don't need to. The point is, this is a detection and this is a bunch of non-detections. They can look at the stamps, but the CNNs are there. They can look at the context. Is there a galaxy nearby? They can look at the coordinates. Is it near the galactic plane? And with all of this diverse type of information, they can make a decent decision and they can do it really quickly. So the goal of my research was to create what I call a virtual research assistant. It's not necessarily fancy, it's not an LLM, it's not like ChatGPT, but it's something that emulates the human strategy because it is very effective doing that job, and something that can look at all of these different types of sources of information. So the virtual research assistant has two jobs. One, rank and prioritize the eyeball list, and two, crop the things that are obviously bad, because we don't want humans to look at these, because it's not a fun thing to do. Now, the VRA has been working in production since September last year, and it's been working really nicely. I'm basically done at this point. Any more work would be diminishing returns. I've managed to crop 80% of the workload of the eyeballers, and we've gone from them looking at 90% garbage to 70% real sources. Now you can see here, oh, by the way, when I say good, I mean extragalactic transients. You can see I am biased. Galactic things are still good if you're a galactic astronomer, but I'm an extragalactic person. So that's what we mean there. Yeah, so it's been working really well, and we could potentially make it even make them look at even a greater proportion of real events. The problem is then we would be losing even more of the galactic events, and I don't want to do that because we are biased, but I don't want us to be that biased. So they're still doing a little bit of extra work. Now, the way that the VRA works is exactly the way that the same analogy I've been using all along. Now, the inputs are what I've described earlier. For the images, the VRA does not look at the images. The CNN has already done that, so I'm actually just using the score that the CNN has given. There's no point in reproducing this, this part. And then the outputs emulate the thought pattern of the eyeballers. When we look at this stuff, we ask ourselves two questions. First, does it look real? Two, does it look galactic? And so that's what the VRA does. And when it gives us the answers, we can put, I'm going to skip the gradient boosting. It's a mathematical trick. And so when you've got your outputs from the machine, you can put your real and your galactic scores in a plot like this. And you can see that the good stuff, what I think is good, the extragalactic events, really fall in that part of the plot, which is real and extragalactic. So it's nice, it's working. Now you might think, okay, that's done a decent job of doing this, but how do you rank? You know, are you using a learning to rank algorithm, maybe some K-clustering? And no, we're using some really newfangled technology here. We're using the Pythagoras theorem. So this is going to be my top rank because I care about extragalactic transients, and this is my bottom rank because it's at the opposite side of the graph. So the way that I rank the alerts is I say, what is the distance between my alert and this corner of the plot? And this has been working really, really well. It was going to be a kind of a placeholder for something fancier, but it's worked so well and it's so understandable by the astronomers using this tool that we've just left it as a distance to that corner of the plot. So the lesson here is that I should really modify this first statement I made at the start of the talk. Progress in astronomy is a partnership between people and technologies, but new technologies, well, the right technologies don't have to be new. Sometimes you can just put Pythagoras at the end of a machine learning model and it will do a decent job. Don't get too carried away with shiny things. Now, obviously, because I've put AI in the title of the talk, some people will probably ask me about ChatGPT. Did you put ChatGPT in there, especially because it's called a virtual research assistant? I'll put it. I'll let you know. I've called it a virtual research assistant before ChatGPT was a big deal. I was writing this grant application years ago, and now everyone thinks it's an LLM, and it really is not. It's just statistics. I mean, LLMs are statistics, but it's not the same kind. So, what about ChatGPT? So, can you tell me what this is? Can you maybe from a distance you can just about make out what this is supposed to be? This is a zoom in on a picture taken with this very phone, the same phone that took the beautiful picture of the Milky Way, and it is a departures board in an airport. I was stuck in Venice airport for 7 hours in July, and I couldn't be bothered getting up, and I'm blind. So I took a picture so that I could zoom in and see if my plane was later than expected. Now, the problem is that my phone has this smart software that creates extra pixels to make the image prettier. The problem is that it was probably trained on making landscapes look more beautiful and faces look snatched. Faces and landscapes don't have a lot of right angles and straight lines. And so when it encountered the words on the board, it turned it into basically wingdings on LSD and made it impossible for me to read the one piece of information I was actually looking for. So why does something like that happen? We're going to look at another milestone of machine learning here. The AlphaGo versus Lee Sedol case. AlphaGo was the, I think, DeepMind algorithm that was trained to beat humans at the game Go. Much harder than chess to teach a machine. So it was a big, big milestone. Lee Sedol was the reigning world champion. And in that competition between the machine and the human, the machine won 4 games, but Lee Sedol won 1. So how does a human win a machine against a machine that has trained so hard? Well, Lee Sedol made a move that the machine did not expect. And so AlphaGo started making really, really, really poor decisions, really not just a little bit stupid, but very stupid. Now, the reason something like this happens is because when we're learning a function, if you've got only a few knobs and dials, you can explore how all of these knobs and dials behave. But if you've got a massive function, a massive model, you cannot explore all of the possibilities of these knobs and dials and how they operate with each other. It's a little bit like trying to explore a gigantic map. Here you've got a screenshot of Civilization 5 with the fog of war, which lifts as you explore the map. You can think of training a machine learning model and exploring that parameter space as trying to lift the fog of war in as many locations as possible so that your model will know how to behave if it finds itself in that location. The problem is that there's something called the curse of dimensionality. The greater the number of dimensions, the exponentially greater the volume, and therefore it's basically impossible to explore even just a small fraction of these large spaces. Professor Neil Lawrence calls this problem Sedolian voids in honor of Lee Sedol, who put AlphaGo in one of these situations. And these Sedolian voids are an issue that I am very concerned about in my job, because they're a problem because your parameter space are big, but also if your training set doesn't take your algorithms in these areas of the landscape, in these areas of parameter space. And this is probably what happened in this case. Now, I care about the weirdest, rarest objects in the universe, which means that it's quite likely that the training sets that computers are trained on will not contain very many of the objects I care about, or none at all. So Sedolian voids galore. Now, these Sedolian voids are a problem across the board, but for things like LLMs and generative AI, they're more of a concern because since they have so many more dimensions, the volume is just so much greater to explore. The other problem of generative AI is that it is a probabilistic kind of model, which means that you put in the same stuff, you can get out different results if you do it over and over again. Sometimes the results are a little bit different, sometimes they're very different. And because many of these models are closed, it's basically impossible to track what's going on. And then the final problem, and that's really an LLM, large language model focused problem, less so with, well, also with pictures, I guess. These models are not trained to be truthful. They're trained to sound human. That's always been the benchmark. People want to emulate humans, to trick humans into thinking a machine is human. But that's not what I care about as a scientist. And these last two problems in particular are really a challenge to reproducibility. And reproducibility is a pillar of science. If you do something really cool, but you don't know how it worked, how you got there, and you cannot do it again, you cannot make it happen again, we might as well be doing astrology, you know, like what's going on. So going back to that statement, earlier I pointed out that the right technology is not necessarily new. What I want to point out here is that new technologies are not necessarily right. New technologies are an opportunity for progress, but progress is not an inevitability. The work of science is to try and test and be skeptical about what we're doing. We need to be as skeptical as we are passionate of these new exciting technologies. Now, finally, I'd want to point out that I think the right technology is not only understandable and reproducible, but also sustainable. Now, I don't have a degree that qualifies me in talking too much about sustainability, but I think it's worth mentioning. As I said earlier, big milestones and big breakthroughs in machine learning came about because of access to large scopes of data and large amounts of compute. Data and compute do not come for free. It might look like they do because they are away from your site in the cloud, in distant data centers. But data and compute require resources, require electricity, require raw materials that need to be dug up from the ground, that have a human cost and that have an environmental cost. So although machine learning is exciting, the best model is the simplest thing that works, even if it's not ML, even if it's a spreadsheet. Because here what we're trying to do is science. We're trying to discover the universe. And I want us to be mindful of the planet that we live on, even when we look up at the heavens. All right, so a couple of thanks to my server wizard and my mentors, and to the Herschel Society for giving me the prize that led to this talk, and of course for the people that invited me here today. Thank you very much.
Thank you very much for your talk, Professor Stevance.
Professor, I got. That's nice. No, it's fine. So usually it's a scam email that calls me professor. So yeah.
Okay.
Do you have any questions?
I've just checked to see if any questions have come through, but they haven't. So we'll be going into our in-person audience if anyone has any. In the technical images that you showed,
Yeah.
so you could see the supernova, and then there was a lot of like spots around. Is that just the example of the millions or in the subtracted image?
Yes, I will go back. Do you mean this one?
The next one.
Yeah.
The supernova and then a bunch of stuff around it.
Okay, that is noise. So this one is a slightly weird effect of subtraction. You can see this bright star there is going to cause this weird dipole thing. These very bright stars that, bright stars there cause a slight artifacts, which are quite obvious. But everything else is noise. And actually, the good point that this raises is, if you've got all of this level of noise that happens in different images, how do you know if something is real versus noise? And that's one of the basic quality cuts that we apply. We say that something has to have a flux that's at least 5 sigma, 5 standard deviations above the flux. So you see that flux, you've got bright points, you've got dark points. So it kind of fluctuates like this. If you plot it just in terms of, not in 2D, but in 1D, just wobbles like this. This bright point has to be at least 5 standard deviations above this standard wobble for us to consider it a potential detection. If it's too close to the noise, well, it's probably just noise.
Worry about like mischaracterization in the data set that you've got? Because you said that they, like, human researchers are selecting which is garbage and which is like different types of events. Is it ever like if sort of mischaracterized, does the model learn to do mischaracterization?
That's a very good point. That's a very good. Can I find? Do I have? Hang on, I'm going to show you a different plot. So the model actually, I re-eyeballed a bunch of data because let me see. So this is an internal report, so it's not nearly as people friendly. Okay, so this is the distribution of some of the alerts before I did some re-eyeballing. You can see the galactic stuff has this weird tail that extends that way. This is proper motion stars. It's a different kind of garbage. That's another kind of garbage. That's the real stuff. And you can see after eyeballing, that tail is gone, or there's a little bit left, but it's mostly gone. That distribution has shrunk. And that's because in that tail, people were putting things in the galactic box that were either garbage or proper motion stars, or just, you know, things that well, proper motion stars mostly. So yes, it does happen. Mislabeling does happen. You can protect yourself against it by two things: by making sure that most of it is correctly labeled, otherwise you're kind of screwed, garbage in, garbage out. But by regularizing your models, so making sure you don't overfit. And actually, the models that I'm using, those gradient boosted things, are really robust, which is quite nice. And it's actually, well, the reason I re-eyeballed these things was because the model was telling me, yo, these are not galactic. What was going on there? So it's actually helped me find specific areas of the data that I needed to look at again to relabel them and actually get a purer sample. Yes.
Would that be the same approach for something to help you identify completely novel things that the model hasn't been trained to identify? Just keep the parameters quite wide?
Yeah, so this kind of stuff is called anomaly detection. And it's something that people work on. In this case, anomaly detection would be not trickier, but it's just because these all fit kind of nicely in this 2D space. There's not a lot of space to go wrong. But anomaly detection is definitely something that people work on to find new transients, where they look at the properties and the distribution of things that we know about, and they create specific algorithms that look at things that basically are orthogonal to that space. And they're like, okay, let's not bin this. Let's have someone look at that in particular. And in the case of the VRA, it's I don't do anomaly detection, but I'm very, very cautious about my garbaging policies. So I only garbage stuff that's really far into that part of the plot. And if something never, because the VRA does update the score as new information comes in, and if something never makes it into one of these corners of the plot where we look at it, I've got a sentinel 2 weeks after the alert that actually shows these. They're not outliers, they're kind of very much inliers, but they're outliers in the sense of they never get a very confident score, so they're a bit weird. And so instead of just garbaging it or discarding them, I make sure that someone looks at them, because there might be something here that we're not used to seeing that the VRA did not recognize. Yeah. Oh, yeah, it's a very good point. I didn't take enough time to explain this. So probabilistic models, I'll say, are not necessarily bad. They can be good, and they do happen in astronomy, but they're only good if you actually understand the probabilities that come out. ChatGPT, that's not the case. So deterministic means I put a number in my function, and my function will always give me the same number on the other side. So it will always give me the same thing, which means that if I give the same number, I can reproduce that consistently. Probabilistic model will give me a probability distribution out. So for example, like a probability distribution just means a scatter of point, in this case in 2D. So if I give a number, and I would get like a bell if I've got a Gaussian distribution. That's not necessarily a bad thing, like I said. In the problem of things like ChatGPT is you don't know what those distributions are, no one's quantified them. It's very difficult to do because they're very expensive models to run and train. So it's definitely not in the scope of many universities. A lot of the compute needed to do this stuff is in industry, not in education centers. So probabilistic models at large, not necessarily bad if you know the distribution, but if you don't know the distribution, then you're shooting in the dark.